Hello and welcome to VHDL lectures. My name is Najim Lawal, and now we shall be discussing VHDL intermediates. Guiding our discussion on VHDL intermediates, we focus on procedure, functions, packages, error management, and test benches in VHDL. Subprograms in VHDL can be implemented using constructs like procedures and functions, both of which must have declarations and a body function. Procedures are sequential computation that returns values in a global object or that have the possibility to update their former parameters, whereas functions are computations that returns values as a return signal of the function, and they do not update their former parameters, nor do they update global variables or objects. Here is the syntax for declaring procedures in VHDL. We use the procedure keyword, we give it an identifier, and then we have a list of parameters. This parameter list, of course, is optional. So here is an example, a procedure called print header. It takes in no parameters, and then it just runs, execute, and implement something. Here is another example that says procedure build. It takes in a few parameters, for example, A, which is a constant of type integer, B, which is a signal that goes in and goes out, and it's a bit vector, perhaps of a given, it's a bit vector, and here is a signal C, a variable of type real, and here we also have a file. Here is an example of how procedures can be implemented in VHDL. So, well, the implementation can be carried out in we can declare VHDL procedures in packages in the architecture, but then when we want to implement it, we can also implement it in the packages and somewhere in the architecture also. Here is an example of VHDL implementation, and implementing like this, we make a reference to the already declared procedure. For example, we say procedure identifier, and we give it the parameter list. We say begin. We can have some declaration of signals and variables before the begin, or some references to some packages that we like to use. And then we have this statement that can be executed sequentially. And we close the procedure by saying end procedure, and we give it the identifier name. Here is a tiny example in which we have a print header that makes references to the IEEE standard text IO. It has a variable, a line. So when this procedure is called, it writes a few string ABC to the header as a header to the file, and then it writes it ends it. So every time you call print header, some strings ABC will be written into a new line, and then it will be, this new line will be written into the header file. Functions and examples of how to declare functions and functions body. Here is the syntax. We use the function keyword, we give it an identifier, and then we have an optional list of parameters, and of course we like to have a return signal. So here is an example. If you like to have a random number generator that returns a floating point number, then we say that or we can test if a particular signal or number, integer value, is an even number or a Boolean number or an odd number. So we return a Boolean data type that tells us yes, that has the value 1 if it is even, or 0 if it is odd. So here is another example of how to implement a function called random number, and we have in it we declare the random number, and we say that we are returning type float. we have a variable that is being declared variable s, which is of type oath, and we compute something that is our random number generator, and we return the variable x, and we close the function random. So this is how we can create a random number generator, and this is perhaps how we can create functions in VHDL, making a reference to the function body or implementing the function body is also done the same way that we did the procedures, in which case we use function keyword, we give the identifier, we have the parameter list, then we declare the return data and the return signal and the data type. We have our declarations that we like to use in it, and then we begin, we execute, and we return. Packages. Packages are the most appropriate places to store your declarations, perhaps some shared variables, some signals, some new data type, some functions, some procedures that we like to use perhaps in many VHDL entities. So most of the time when we work in VHDL, we have a library called IEEE. In this library, there are many packages, but when you are synthesizing and simulating your design, there will be a library created for you called library works, and all of your designs will be implemented in this library, and you can actually create your own packages that will be attached to your library, or that you can share among your colleagues or your team members. So if you can create a package this way by saying that you use a package keyword, the keyword package, you give it an identifier, and then you have your declaration. Your declarations can include signal declaration, shared variable declaration, functions, procedures, new data types, or extension of some data types. So the kind of stuff you can include are listed here. We have access to files, you have component declaration, you have aliases and attributes and constants and RAM types and signals declaration. Package bodies, more or less like a declaration or body implementation of functions and procedure, is done the same way. You declare package body and then identifier of the package that you have created. So you can have a file where all your packages are, where you have a package declaration and all this attached to it, and then you can have another file, or perhaps in the same file where you declare the package, you can actually implement it there. So you can have a package where you declare entities and every other thing, and then you can also have other files where you have the implementation of these entities and these packages and everything like that. So here is an implementation of a package. You declare package body, the identifier that attaches to the particular package you like to implement, and then the declaration, which perhaps is implementation of the subprograms of the functions and perhaps accesses to some files that might be necessary in the package. Okay, so here is a very good place for us to make a subprogram declaration. Here is a good place to make implementation of subprograms, to declare types, and then to assign values to types, or to assign values to signals and other signals and registers that we like to create. Here is an example of a package declaration and implementation. Here I have a package called my package. Okay, in this package I have a new type called small. It's an integer range from 0 to 4096 or 4095, and then I have a procedure which is it's an increment. It increments the data type small, so it has a parameter that is a signal of type A. It's an input and output signal, and then it's a signal called A. It's an input and output, and it has a data type small. I have a function that can decrement, that can decrease this signal also. So I call it s_dec. It has a parameter b that is of type signal, and it returns another signal of type small. Another operator by saying end package. Somewhere else, perhaps in the same file, I would like to implement this package, and I do this by saying package body, and then I give it the name of the package that I would like to implement. And then I say that here is where I would like to have implementation of my procedure, and here is where I would like to have implementation of my function. So now you can see a connection between defining new data type, defining procedures, and defining functions. And for example, in this package body now, I have an implementation of the procedure s_inc, which I have already declared when I was declaring my package. So here I have A coming in as a signal, as a port in and out, and then it's of type small. So the definition of small has already been given in the declaration of a package. So it's now easy for me to use, and all my colleagues that have access to this package can easily declare small that counts from 0 to 4096. And then I have an implementation of this procedure that says begin. A is to be updated as A+1. So this is a port, an in-out port, and every time this procedure is called, the value of A that is given into it as an input will be updated at supply back. Here is a function declaration, also a function implementation that says that s_dec, it takes in the signal B of data type small, and then it returns another signal of data type small. In this, I do begin, I calculate the update by saying that return B-1, and then I close the function. Error management in VHDL. The construct for doing this is by using assert statements, and assert statements are sequential statements that are usually used in test benches and in simulation to know if a particular condition has been satisfied. So we have two kinds of constraints. These are functional constraints and these are time constraints. These are the kind of constraints that can be tested by assert statements. So if a condition is satisfied and confirmed or asserted, the simulation continues. So assert that 2 + 2 is 4. As long as 2 + 2 is 4, the simulation continues. But if the assertion fails, if condition is not satisfied, whether as a function of time or a functional condition, so assert that this procedure is completed within 20 nanoseconds. So that's a constraint on time. If that constraint is not fulfilled, assertion fails, and then an error or a report will be generated, and the kind of report that is generated or the condition, the severity can be specified. So here is the syntax for implementing assert statement. We have the assert condition, we raise the kind of report that we like to say, and then we raise the severity level based on what we are implementing. So here is an example of what message can look like. Messages and error levels are displayed in the simulator test console for feedback. Assert statements can be sequential or it can be concurrent statements. Assert statements should only be in the test benches because assertion cannot be synthesized in hardware. So here is an example of a assert condition. Assert that s is less than or equal to a particular value. Assert that input 1 is not equals to 0, and at the same time input 2 equals 1. Assert that now at this current state the time is exactly 200 nanoseconds. The kind of report that can be given as a message is this. This is the syntax, and here's an example. Report output x is out of range. If x is greater than a particular value, report that the value of input 1 and input 2 are not valid, and if time is now 200 nanoseconds, report that simulation has been completed. Furthermore, in error management in VHDL, as an intermediate concept or knowledge that somebody should know when dealing with VHDL and when simulating with VHDL, you like to be able to know the severity level of an error that is being generated. So when you just want to give a note that time is now 200 nanoseconds, maybe you like to print that in blue because it's just a feedback. Warning might be printed in yellow, and it can be some condition that it's good to know, and it can have an impact in the future. For example, if you're adding two numbers together, if you're adding 8 bits and another 8 bits together, you have the potential of generating a 9-bit, but if the value is to be assigned to another 8-bit value, then you might want to generate a warning that there is a potential that you have an overflow, and then the value may not be correct. An error is usually printed in red, but then you can, and then the system can be forced, cannot be forced to continue. So when an error exists, for example, if you are trying to read a particular file that doesn't exist or beyond a particular level, and then a failure in the system simply hangs the system, and then you say that it cannot continue anymore. It's also printed in red. Okay, a failure is an example of, for example, if time is no longer satisfied, or if a division, or if there is an operation that is not allowed. For example, if you are trying to read a particular memory level that is larger than the number of memory locations. So default severity, if nothing is given, is error, which means this is simulation stops. The report clause can be used with severity without an assertion. So perhaps you just want to execute, and whenever a particular if condition is executed, you simply want to report what has happened. So inconsistent data type, severity failure, or severity given. Whatever severity you like to use that can force the simulation to stop. So now we have a assert clause can be used also as concurrent statement, and it can be given a label. So here is an example of how to use assert statement in a VHDL. If, for example, we have an entity called assert_example, and then we have signals coming in A and B and an output Q. We have an architecture example associated with the entity assert example, and then we begin the implementation of the architecture, and we say that assert that A is not equal to 1 or B is not equal to 1. Report that if this is not sustained, if this assertion fails, we like to report that A and B are 1, or both of them are 1 at the same time. So then we like to give a warning. Perhaps there's something that's going on that you don't want the value of A and the value of B to be 1 at the same time. Okay. Then we can have a procedure also. It's a way of including assertion inside a procedure. So the first assertion is implemented as a parallel statement in the architecture, but now we can have a sequential statement in the body of a process. So we have a process AB that is these two assertion implementation are actually identical or doing the same thing. So now we have a process that is included now that is sensitive to both signals A and B, and then if A equals to 1 or B equals to 1, then we raise an assertion and say that assertion is false, and then we make a report that says that A equals to 1 or B equals to 1. You just write the report and we go on. Okay, so we end the process and then we can continue. Test benches in VHDL, it's it's perhaps the first place to start. So before you design a component in VHDL, you probably want to have a very good idea about how to test the component. So these are the intermediate things. So now you know how to create entities, you know how to create architectures, you know how to use a lot of things, a lot of constructs in VHDL, you know how to test if a particular statement is correct or not. You know how to wrap your functions and procedures together in a package. Now you also like to have an entity that you like to test, unit under test. You want to be able to generate stimuli that can be used to test this entity, and you like to be able to analyze the results. To do this, you need at least 3 components. The unit you'd like to test, it can be anything. It can be a PWM signal decoder, it can be video signal generator, it can be a clock counter, it can be UART interface, it can be different parts of your designs or a complete design wrapped together. And then you have the stimuli generator, you have the response tester. When you talk about the response tester, you like to have a mimicry of a word, or a limitation, a virtual environment of a real life environment, of a real life situation in which your design will be connected to and be working. So if you are doing image analysis, then you like to have a mimicry of a camera or of a monitor, and then you like to be able to analyze the PWM signal, also something that can help you to generate PWM signals. You like to be able to simulate or mimic a clock or a reset situation. You like to be able to generate control signals. You should be able to have a ability to read and write data to memories and perhaps to text files. Something that wraps around your unit under test, assuming that your unit under test has not even been developed, but you know the interfaces it's going to have. When we talk about tester, then you should be able to have a truth table, an experience, or a logic, or even something from a software that's already existing, and you know the true value of this operation. So when you have this at the back of your mind, then you can generate a test bench, say a waveform analysis, or result files that you can use to test against your implementation. So here is an example of what your test bench can look like. You make reference to the IEEE and the relevant packages that you need. Usually you have no ports, and then this is the universe as far as your design is concerned. But then here you can create generics that can be used when you are authenticating some other components. Here is an example of how to create clock in test benches and how to create a reset in test benches. So I have a label here, clock underscore generate. It's a process that is sensitive to the clock. I have a constant, the pulse width is a time that is 50 nanoseconds, which means that I will be generating 10 megapixel clock. So the clock period is 100 nanoseconds, and then I have a begin. If the clock is 0, then assign 1 to it after the pulse width, and then assign 0 to the clock after 2 times pulse width. So it continues to oscillate between 0s and 1 throughout the simulation of your design. And here is another way of simulating a reset. So assuming that you initiate simulation, then the reset will be given to a particular level 1, and then it will remain at that level until it is given a particular level 0, which in this case is supposed to be 60 nanoseconds. One thing you will notice in this example is the use of the word after, or the construct after. This word is not, or this construct is not synthesizable in VHDL, and that's why it's appropriate to put it in a test bench. So Here is a hint. The unit under test should be something that you like to test. It can be very simple and it can be very complicated, and even for complicated design you can break it down into components and sub-modules, and each of them can be tested individually. You like to connect to other modules and devices and perhaps through the I/O pins. So the unit under test connects to the rest of the world through the FPGA I/O pins. The unit under test should contain all of the ports and generics that you like to use, but then you can update these things using from the test bench. The clock should be very close to the final implementation or the clock constraint of the timing requirement of your design. And here, of course, we need to have the concept of reset at the beginning of our VHDL design life. We need to have the concept of resets in our design, because you like to bring the state, you like to start off your design from a known state, the state reset. So this brings us to the end of VHDL intermediates, and we have discussed procedures, functions, how they connect together, what are the differences between them, how they can be wrapped up together in a package, how designs can be tested, what kind of errors can be raised or can result in a VHDL design. Thank you for joining us. Bye.